Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
Across the outermost layer of modern astronomy lies a continuous watch of the sky that does not focus on a single star or planet but on the entire dome of darkness itself. This region is not a place in space, but a framework of observation built from wide fields of view, repeated scans, and patient accumulation of light. Large survey telescopes operate night after night, sweeping broad swathes of sky, with cameras designed to register faint points that shift slightly between exposures. These systems do not begin with interpretation, they begin with coverage. The goal is to notice anything that does not stay still. In this environment, most of what appears is familiar. Stars hold their relative positions, distant galaxies remain fixed, planets move, but their paths are known and slow. Against this stable background, anything new is defined first by motion, and only later by meaning. The surveys are arranged to favour repetition over detail. Each patch of sky is visited again and again, sometimes minutes apart, sometimes days. Light is collected in measured intervals, converted into digital records and compared against earlier frames. Software searches for points that change position or brightness beyond expected limits. This process is deliberately simple. It does not assume what an object is, it flags difference. In this outer observational layer, difference is enough. A moving point is logged, assigned a temporary identifier, and passed along for human review. The system is designed to miss nothing important, even at the cost of capturing many things that later prove ordinary. This approach reflects the scale of the task. The sky contains billions of sources, and the faintest detectable objects often hover near the limits of sensitivity. Survey instruments balance exposure time against sky coverage. Short exposures reduce blur from motion and allow frequent revisits. Long exposures reveal fainter objects but slow the cadence. Modern surveys choose a middle path optimized to catch small bodies moving through the solar system while still mapping distant structure. The result is a steady stream of candidates, most of them asteroids bound to the Sun following predictable paths shaped by gravity alone. The outer survey environment also includes automated alert networks. Once a moving object is detected, its position and brightness are distributed rapidly to observatories around the world. This networked response allows confirmation and refinement. A single telescope provides a hint. Many telescopes provide a track. The earlier this coordination begins, the better the chance of understanding the object before it fades from view. For fast-moving or faint bodies, time is limited. Days can matter, sometimes hours. Within this observational layer, there is no assumption of rarity. The systems are built with the expectation that the sky will continue to change in small ways. New asteroids are found regularly. Comets appear from the cold outskirts and grow brighter as they approach the Sun. Occasionally a more unusual visitor passes through. The surveys are indifferent to category. They respond the same way to everything that moves. This neutrality is essential. It ensures that unexpected objects are not filtered out by preconceived ideas of what should exist. The instruments themselves operate under known constraints. Atmospheric turbulence blurs images. Moonlight raises background brightness. Weather interrupts coverage. Survey schedules account for these factors, but they cannot eliminate them. As a result, detections carry uncertainty from the start. Position measurements have margins of error. Brightness varies with viewing angle and distance. In the outer survey layer, these uncertainties are accepted. Precision comes later. At this stage, the task is recognition, not explanation. The naming conventions applied at detection also reflect this provisional state. Objects receive temporary designations that encode the time and source of discovery. These labels are functional rather than descriptive. They mark an entry in a database, not a conclusion. Only after further observation does an object earn a more permanent classification. In the earliest moments, even the distinction between asteroid and comet may remain unclear. The surveys record what is seen, not what is assumed. This outer observational region extends beyond any single facility. It includes ground-based telescopes spread across continents coordinated to maximize coverage of the night sky. It also includes space-based observatories that operate above the atmosphere free from weather and air glow. Together, these instruments create a layered watch with overlapping capabilities. Some excel at depth, others at speed. Some monitor the same regions repeatedly, others fill in gaps. The combined effect is a near-continuous awareness of changes across much of the visible sky. The pace of discovery in this environment has increased steadily over recent decades. Improvements in detector sensitivity, computing power, and data sharing have transformed what was once a slow manual process into a rapid automated flow. Objects that might have gone unnoticed in earlier eras are now flagged within hours. This acceleration does not change the nature of the sky, but it changes the human relationship to it. Motion that once passed unseen is now recorded and archived. Yet even with these advances, the surveys remain limited by geometry and chance. They are most sensitive to objects that pass near the Earth or move against dense star fields where motion is easier to detect. Objects approaching from directions close to the sun's glare are harder to find. Others move too slowly at great distances to stand out. The outer survey layer is comprehensive but not complete. It is a sampling shaped by design choices and physical limits. In this broad observational context, the appearance of a new moving point is not dramatic. It is one entry among many distinguished only by its measured properties. The surveys do not announce significance, they provide data. Any sense of importance arises later after patterns emerge and comparisons are made. At the moment of detection, a moving object is simply a moving object. This restraint is deliberate. It preserves clarity. By separating detection from interpretation, the survey environment ensures that each object begins its recorded existence on equal footing. Only after sufficient measurements accumulate does its path through space become clear. Only then does it move from the outer layer of raw observation toward more focused analysis. For now, within this wide and patient watch of the sky, the object exists only as a faint point of light shifting slightly against a background that otherwise remains still. Within the steady background of routine detections, the circumstances surrounding the identification of 3I/Atlas unfold without ceremony. The object first appears as a faint unresolved point during a scheduled survey pass, recorded alongside countless other sources that night. Its brightness falls near the lower edge of sensitivity, and its shape is indistinguishable from a star at that scale. Nothing about its appearance alone sets it apart. What draws attention is motion measured across successive images taken hours apart. The displacement is small but consistent, exceeding the threshold that the detection software is designed to flag. The initial record consists of time-stamped positions on the sky expressed against a grid fixed to distant stars. These measurements carry uncertainty from atmospheric distortion and detector noise, but the motion is clear enough to survive automated filtering. The object is provisionally tagged and entered into an alert stream shared with follow-up observers. At this point, it is treated no differently from a newly found asteroid. Its provisional designation encodes the date of detection, and the survey responsible serving as a placeholder rather than a statement of nature. As additional observations arrive from the same facility later that night, the track lengthens. The motion appears faster than typical for main belt asteroids, which usually drift slowly against the star field. Still, speed alone is not decisive. Near-Earth objects can move quickly, especially when close to the planet. The early data allow only a short arc of motion insufficient to define a reliable orbit. In this phase, the object exists as a hypothesis, a candidate trajectory awaiting confirmation. Within the next observing window, other telescopes respond to the alert. They target the predicted location based on the preliminary motion estimate scanning a small region of sky where the object is expected to appear. Success is not guaranteed. Prediction errors grow quickly when based on limited data. In this case, the object is recovered within the search area, providing new positions separated by additional hours. Each successful recovery reduces uncertainty and tightens the provisional path. The accumulation of observations over several nights allows for the first rough orbital solution. This calculation uses classical mechanics fitting the measured positions to a path governed by gravity. At this stage, the solution is tentative. Small changes in assumed distance can alter the inferred trajectory significantly. Astronomers are cautious, updating the solution with each new data point. The object's motion relative to the Earth and Sun becomes clearer, revealing a steep approach angle that differs from most bound asteroids. Throughout this process, the data flow remains procedural. Measurements are reported, residuals examined, and uncertainties tracked. There is no immediate declaration of novelty. The systems are designed to avoid premature classification. Instead, they focus on internal consistency. Do independent observations agree within expected error? Does the object reappear where predicted? Does the brightness change smoothly with geometry? Each affirmative answer builds confidence that the detection is real and that the motion is understood at a basic level. As the orbital fit improves, one parameter begins to stand out. The object's velocity relative to the Sun appears unusually high. Even accounting for measurement uncertainty, the speed exceeds what is typical for objects bound to the solar system at similar distances. This observation does not yet imply an interstellar origin, but it prompts closer scrutiny. The discovery circumstances shift subtly at this point, from routine tracking to focused attention. Additional observing time is allocated, and the cadence of follow-up increases. The brightness measurements collected during discovery also undergo review. Photometry. The measurement of light intensity is checked for signs of variability that might suggest rotation or activity. In the earliest data, the brightness remains steady within error margins. No diffuse glow or extended structure is visible. The object remains point-like, consistent with a small solid body rather than an active comet. This absence of visible activity is noted but not emphasized. Many comets show no activity at large distances. The discovery pipeline includes safeguards against false positives. Known objects are cross-checked against catalogues to ensure the detection is not a rediscovery of an already tracked body. Artifacts caused by cosmic rays, detector defects, or background noise are filtered out through pattern recognition and human review. In the case of 3I/Atlas, these checks are satisfied. The motion is coherent across independent instruments and nights. The object is confirmed as new. As confirmation solidifies, the provisional designation remains, but internal notes begin to reflect growing interest. The discovery circumstances now include context. The object is approaching from a direction that suggests it is not part of the usual populations. Its path does not align with the plane where most asteroids reside. This geometric detail emerges naturally from the data without interpretation. It is simply a statement of orientation recorded as part of the evolving solution. The discovery phase is constrained by time. Objects on fast trajectories can fade quickly as distance increases or viewing geometry worsens. Observers prioritize collecting enough data to secure the orbit before the object becomes too faint. In this case, the discovery window spans several weeks, during which observations continue whenever weather and scheduling allow. Each additional measurement refines the circumstances of discovery, transforming an initial detection into a well-documented event. During this interval, the object's name becomes standardized. The provisional designation 3I/Atlas is adopted within the reporting system, reflecting both its interstellar candidate status and the survey responsible for its detection. The naming follows established conventions and carries no implication beyond classification. It serves to distinguish this object from others and to anchor subsequent discussion to a specific data set. The discovery circumstances also include what is not seen. No sudden brightening occurs, no tail develops, no fragmentation is detected. These absences are noted alongside positive measurements forming a balanced record. In astronomy, non-detections can be as informative as detections, especially when assessing physical processes. At this stage, however, they remain observations rather than explanations. By the end of the discovery phase, the object's existence as a distinct trackable body is secure. Its path through the sky is defined well enough to predict future positions. Its brightness is measured across multiple filters. Its motion relative to the Sun and Earth is quantified within known uncertainties. The circumstances of its discovery are now complete in a technical sense. They consist of a timeline of detections, confirmations, and refinements, all grounded in observation. This phase concludes without resolution of deeper questions. Discovery establishes that the object is there and that it moves in a particular way. It does not yet address why it moves as it does or what it is made of. Those inquiries belong to later stages of analysis. For now, the discovery circumstances stand as a careful record of how a faint moving point transitions from anonymous data to a recognized object within the astronomical community ready for further study. With the discovery arc extended across multiple nights, attention turns to the object's initial orbital parameters, which describe how it moves through space relative to the Sun. These parameters are not physical traits, but mathematical descriptions derived from position and time. They form a bridge between raw observation and physical interpretation. In this region of analysis, the focus remains on motion, alone stripped of assumptions about composition or origin. The first step is to determine distance. Apparent motion across the sky combines true velocity with perspective effects caused by the Earth's own movement. By comparing observations from different points in the Earth's orbit and from different locations on the planet, astronomers estimate how far away the object is at each observation time. This process relies on parallax, the apparent shift of position against distant stars when viewed from different locations. For nearby objects, the shift is measurable. For distant ones, it is subtle. In the case of 3I/Atlas, the parallax signal is small but detectable over time, allowing distance estimates with defined uncertainty. Once distance is constrained, velocity follows. The object's speed relative to the Earth is inferred from how quickly its position changes. This speed is then transformed into a velocity relative to the Sun by accounting for the Earth's own motion. The result is a vector, meaning it has both magnitude and direction. Early solutions show that this solar relative speed is high compared to most known small bodies at similar distances. This observation emerges directly from the calculations without adjustment or interpretation. The orbital path itself is described using a small set of standard parameters. One of these is eccentricity, a measure of how stretched an orbit is compared to a circle. A circular orbit has low eccentricity, while a very elongated path has high eccentricity. Another is inclination, which describes how tilted the orbit is relative to the plane defined by the Earth's path around the Sun. These terms are technical, but their meaning is straightforward. They locate the object's motion within three-dimensional space. The preliminary eccentricity derived for 3I/Atlas is unusually high. The value approaches and appears to exceed the boundary that separates bound orbits from unbound ones. In practical terms, this means the object's path is not closed around the Sun. Instead of looping back repeatedly, it follows a single passage arriving from afar and continuing outward again. At this stage, the exact value remains uncertain, but repeated solutions converge on the same conclusion. The orbit does not appear to be gravitationally bound to the Sun. Inclination adds another layer. The object's path is steeply tilted relative to the plane where most planets and asteroids reside. This plane, known as the ecliptic, contains the majority of solar system material because it reflects the original disk from which the planets formed. Objects bound to the Sun can have tilted orbits, but extreme tilts are less common. The inclination of 3I/Atlas places it well outside the densest populations, reducing the likelihood that it originated within the known asteroid belts. Another key parameter is the direction of approach. By tracing the orbit backward, astronomers identify the region of the sky from which the object appears to arrive. This direction is defined relative to the Sun's position and the background of stars. It does not point to a specific source but provides a context. For bound objects, this direction is often linked to known reservoirs such as the outer cloud of icy bodies surrounding the solar system. For 3I/Atlas, the inbound direction does not align clearly with these regions. It is instead consistent with a trajectory shaped primarily by motion through interstellar space before entering the Sun's influence. Uncertainty is an inherent part of these early orbital solutions. Each measurement carries error, and these errors propagate through the calculations. Astronomers quantify this uncertainty using ranges rather than single values. For example, the eccentricity is not one number, but a span within which the true value likely lies. In the case of 3I/Atlas, even the lower bound of this range remains above the threshold for a bound orbit. This robustness strengthens confidence in the unbound classification even before further refinements. The calculations assume gravity as the only force acting on the object. This assumption is standard at this stage. Deviations from gravitational motion are considered later once the baseline orbit is established. By fitting the observations to a purely gravitational model, astronomers create a reference against which future discrepancies can be measured. In this sense, the initial orbital parameters are provisional by design. They define what the motion would look like if no additional forces were present. As more data accumulate, the orbital solution is updated repeatedly. Each new observation slightly adjusts the parameters, narrowing uncertainties and improving predictive power. The process is iterative rather than linear. Early solutions may shift noticeably as the arc lengthens. Later updates tend to produce smaller changes. For 3I/Atlas, the early convergence toward an unbound, highly inclined orbit remains stable across updates. The core features of the motion persist despite refinements. The time of closest approach to the Sun is another derived parameter. This moment, known as perihelion, marks when solar gravity has its strongest influence on the object. The calculated perihelion distance for 3I/Atlas places it outside the inner planetary region. It does not approach as closely as many comets do. This detail is important for understanding thermal effects later, but at this stage it serves only as a geometric descriptor of the orbit. The initial orbital parameters also allow prediction of future positions. These predictions guide continued observation. If the object appears where predicted confidence in the solution grows. For 3I/Atlas, subsequent recoveries align closely with forecasts based on the evolving orbit. Residuals, the differences between predicted and observed positions, remain small and systematic. This agreement indicates that the gravitational model captures most of the motion accurately, at least over the observed interval. Despite this success, astronomers remain cautious. Short observational arcs can sometimes mimic unbound orbits for objects that are actually bound but poorly constrained. However, the speed and direction parameters for 3I/Atlas reduce this risk. The object is moving too fast on too steep a path for a bound solution to fit the data, without implausible adjustments. As a result, the initial orbital parameters already suggest a rare category. At the end of this phase, the object's motion through space is described with clarity, though not with finality. The parameters outline a path that enters the solar system from outside, passes through once, and continues onward. This description is based entirely on measured positions and well-tested mechanics. It does not yet address physical causes beyond gravity. It simply defines how the object moves. By establishing this baseline, the analysis prepares the ground for deeper questions. Any future deviations from the predicted path will stand out against this gravitational framework. For now, the initial orbital parameters serve as a precise map of motion-guiding observation and framing understanding while remaining open to revision as new data arrive. With the initial orbital parameters established, analysis moves to classification, which asks whether the object belongs to the solar system or merely passes through it. This step does not introduce new forces or physical models. It relies on comparing the derived orbit to the criteria that separate bound from unbound motion under gravity. The distinction is formal and conservative, grounded in long-established celestial mechanics. A bound object follows an orbit that closes on itself. Even if stretched and tilted, it remains gravitationally tied to the Sun, returning after completing a loop that can last years, centuries or longer. An unbound object, by contrast, approaches once and departs its path defined by a single encounter. The mathematical boundary between these cases is precise. When an object's total energy relative to the Sun is negative, it is bound. When the energy is zero or positive, it is not. This energy is inferred from speed and distance, both derived from observation. For 3I/Atlas, the calculated solar relative speed at large distance exceeds the local escape speed from the Sun's gravity. Escape speed is the minimum velocity needed to leave a gravitational field without falling back. At the object's inferred distance during observation, this speed is well known. The measured velocity remains higher than this threshold even when uncertainties are taken into account. This result is not marginal. It persists across different solutions and independent analyses. Another way to express the same conclusion is through eccentricity. In gravitational theory, a bound orbit has eccentricity less than 1, while an unbound path has eccentricity equal to or greater than 1. The values calculated for 3I/Atlas lie above 1 by a margin that cannot be explained by measurement error alone. This parameter summarizes the motion in a single number, but it reflects the same underlying reality as the energy calculation. Classification also considers the object's inbound velocity, far from the Sun, sometimes called the excess velocity. This value represents how fast the object would be moving relative to the Sun if solar gravity were removed entirely. For bound objects, this value is 0 by definition. They have no residual speed at infinite distance because they remain tied to the Sun. For 3I/Atlas, the excess velocity is non-zero and significant. It indicates that the object carried momentum into the solar system from outside. These criteria together define interstellar status. The object is not merely on a long-period cometary orbit originating from the distant cloud of icy bodies surrounding the solar system. Those objects, while distant and slow to return, remain bound. Their inbound velocities are low-shaped almost entirely by the Sun's pull. 3I/Atlas arrives already moving faster than the Sun can retain. This difference marks a change in origin rather than degree. The classification process also examines whether any plausible past interactions could explain the observed motion while remaining bound. For example, a close encounter with a giant planet can accelerate an object, altering its orbit dramatically. Such gravitational assist can eject bodies from the solar system. In principle, an object could appear unbound now while having originated locally. To assess this, astronomers trace the orbit backward, in time accounting for the gravitational influence of known planets. When this backward integration is applied to 3I/Atlas, the results show no close encounters capable of providing the required energy increase. The path does not intersect regions where such interactions are likely. The object approaches the inner solar system on a trajectory that bypasses the major planets. This absence of plausible ejection mechanisms strengthens the interstellar interpretation. The object's speed is not the product of recent scattering. It appears intrinsic. Directionality provides an additional check. Objects ejected from the solar system tend to leave along paths influenced by the geometry of planetary encounters, often clustered near the plane of the planets. 3I/Atlas approaches from a direction that is not strongly associated with these regions. Its steep inclination and inbound orientation are more consistent with a random interstellar trajectory than with a locally sculpted one. This observation does not pinpoint a source but supports the broader classification. Uncertainty is acknowledged throughout this process. Measurements have error bars. Models make assumptions. Astronomers consider whether small systematic biases could shift the solution into the bound regime. For 3I/Atlas, such shifts would require changes well outside the plausible range of error. The classification is therefore made with high confidence even at this early stage. The object is designated as interstellar, marking it as originating beyond the Sun's gravitational domain. This designation carries procedural implications. Interstellar objects are rare within the observational record, and their fleeting passage offers limited opportunity for study. As a result, the classification triggers coordinated efforts to gather additional data across wavelengths. However, the classification itself remains a statement about motion, not composition or behavior. It does not imply that the object is unusual in form, only that its path is not solar-bound. The interstellar label also requires care in communication. It is not a claim about intent or origin in a specific stellar system. It simply states that the object is moving through interstellar space and happens to pass through the solar system. The vast distances between stars mean that such objects can travel for millions or billions of years before encountering another system. The classification does not assign age or history beyond this general context. Within the scientific framework, interstellar objects provide a sample of material formed elsewhere. Yet this implication remains secondary at the classification stage. The immediate concern is accuracy. By applying consistent criteria, astronomers ensure that the label reflects the data rather than novelty. The same standards applied to 3I/Atlas would apply to any object with similar motion. In this sense, the classification is routine even if the outcome is rare. As observations continue, the interstellar status remains stable. Subsequent measurements refine the orbit but do not alter its fundamental character. The object remains unbound in all credible solutions. This stability allows researchers to proceed with confidence to subsequent layers of analysis, knowing that the object's motion cannot be explained solely within the solar system framework. The classification phase concludes with a clear statement of what is known. 3I/Atlas follows an unbound trajectory through the solar system. Its speed, direction, and energy relative to the Sun exceed the limits of gravitational binding. No known planetary interaction accounts for this motion. These facts establish its interstellar nature without invoking assumptions beyond observation and established physics. What remains unknown is how this object responds to the solar system environment as it passes through. That question belongs to the next region of inquiry. Having established that the object is interstellar attention, shifts outward again to the geometry of its entry into the solar system. This region concerns spatial relationships rather than forces or materials. It describes how the object's path intersects the Sun's domain, and how that path is oriented relative to familiar structures. Geometry here is descriptive. It sets the stage without assigning cause. The solar system occupies a small region within interstellar space defined loosely by the extent of the Sun's gravitational influence. There is no sharp boundary. Instead, gravity weakens gradually with distance. An interstellar object approaches along a trajectory shaped initially by its motion through the galaxy, and only later by the Sun. Far from the Sun, the object's path is nearly a straight line. Curvature increases as it enters regions where solar gravity becomes significant. The direction from which 3I/Atlas approaches is defined in celestial coordinates tied to the background stars. This direction is not aligned with the plane of the planets. Instead, the approach angle is steep, indicating that the object enters from well above or below the flattened disk where most solar system bodies reside. This geometry is typical of interstellar visitors which arrive from random directions set by their galactic motion, rather than by solar system formation processes. As the object moves inward, its trajectory bends smoothly under the sun's pull. This bending follows predictable rules. The closer the object comes, the more its path deviates from a straight line. The amount of bending depends on speed and distance. Because 3I/Atlas carries substantial inbound velocity, the curvature is modest. The path resembles a shallow arc rather than a tight turn. This geometry is consistent with an object passing through, rather than one being captured. The plane of motion remains fixed in space, defined by the object's velocity vector and the sun's position. This plane intersects the planetary plane at a sharp angle. The intersection line marks where the two planes cross, but the object does not linger near this region. It moves quickly through spending little time near the densest populations of planets and debris. This reduces the likelihood of close encounters that could significantly alter its path. Distance scales matter in this region. The object's approach begins far beyond the orbits of the giant planets, in a region where the sun's influence competes with that of passing stars and the general gravitational field of the galaxy. As it enters the realm dominated by the sun, its path becomes increasingly centered on the sun rather than on its original galactic frame. This transition is gradual and continuous, not abrupt. The point of closest approach, or perihelion, lies outside the inner planetary system. The object does not pass near the Earth or the terrestrial planets. Its minimum distance from the Sun places it closer than the outer planets, but farther than many comets that develop visible activity. This geometric fact constrains which environmental factors become relevant later. At this stage, it is simply a measure of proximity. The timing of entry is also part of the geometry. The object arrives when the Earth occupies a particular position in its orbit. This relative positioning affects how the object is observed from Earth, influencing apparent speed and brightness. From some vantage points, the object's motion appears faster against the sky, from others slower. These effects are accounted for in orbital calculations, but belong to geometry rather than physics. As the object moves along its inbound leg, it crosses regions of varying particle density. The outer solar system contains sparse dust and gas remnants of the primordial disk and material shed by comets. The density is extremely low, far lower than any vacuum produced on Earth. For the purposes of motion, this environment offers no resistance. The geometry of the path is unaffected by these particles. They are noted only because they define the medium through which the object travels. The Sun itself acts as the central reference point for describing this geometry. Positions are measured relative to it, and distances are expressed as separation from it. This choice simplifies description, but does not imply that the Sun dominates all influences. At large distances, other stars and the galaxy matter. Closer in, the Sun dominates. The geometric description transitions smoothly between these regimes. The object's outbound path mirrors its inbound path in a geometric sense, forming a hyperbolic curve symmetric around the point of closest approach. This symmetry holds under gravity alone. Any deviation from this symmetry would indicate additional influences. At this stage, the focus remains on the idealized gravitational geometry, which provides a reference against which observations can be compared. Projection effects complicate the apparent geometry when viewed from Earth. The object's true three-dimensional path is projected onto the two-dimensional sky. This projection can make the path appear curved or straight depending on perspective. Astronomers account for this by reconstructing the full spatial trajectory from multiple observations. The resulting geometry is independent of viewing angle, though it is inferred through it. The solar system's structure also includes regions of resonances and gravitational gradients, particularly near massive planets. 3I/Atlas passes well outside the strongest of these zones. Its geometry keeps it clear of close planetary approaches. This is not a matter of chance alone, but a consequence of its steep inclination and timing. The object's path threads through the solar system without intersecting its most dynamically active regions. As the object continues inward, the sun's radiation environment intensifies. Light and heat increase with decreasing distance. While these factors do not alter geometry directly, they are spatially organized around the sun. The geometric description notes only that the object moves along a path that carries it through progressively brighter and warmer regions. The rate at which these conditions change depends on speed and distance, both geometric quantities. The description of entry geometry ends with a clear spatial picture. An interstellar object arrives from a direction unaligned with the planetary plane, follows a shallow curved path under solar gravity, reaches a moderate minimum distance, and departs along a symmetric outbound leg. This path is defined by measured positions and well-understood mechanics. It is a map of where the object goes, not of what it is or how it responds internally. By completing this geometric layer, the analysis establishes the spatial context within which all subsequent behavior occurs. The object's interactions with gravity radiation and any other influences are constrained by this path. For now, the geometry stands alone, a neutral description of motion through space, providing the framework for examining how the object behaves as it continues its passage through the solar system. With the entry geometry defined, analysis turns to expected passive dynamics, which describe how an object should move if gravity is the only significant influence. This region establishes a baseline rather than a claim. It outlines the motion predicted by well-tested laws when an object has no active response to its environment beyond mass and inertia. The purpose is to define normal behavior before examining any departures from it. In passive dynamics, the object is treated as a point mass. Its size, shape, and composition are irrelevant to its path as long as no additional forces act. The sun's gravity dominates with smaller contributions from planets depending on distance. The resulting motion follows a smooth curve fully determined by initial position and velocity. Once these are known, the future and past path can be calculated precisely within the limits of measurement uncertainty. For an interstellar object like 3I/Atlas, passive dynamics predict a hyperbolic trajectory. The object approaches from far away with a given inbound velocity, accelerates as it falls into the sun's gravitational, reaches maximum speed near closest approach, and then decelerates as it climbs out again. The inbound and outbound paths are mirror images in time, symmetric around the moment of closest approach. This symmetry is a hallmark of purely gravitational motion. The speed variation along this path is predictable. Far from the sun, the object moves at its excess velocity set by its interstellar motion. As it draws nearer, gravitational acceleration increases its speed. The increase depends on distance, following a simple inverse relationship. At perihelion, speed reaches a maximum. Afterward, the same gravitational field reduces the speed by the same amount, returning it to its original excess velocity at large distance. No energy is gained or lost in this ideal case. Direction changes are also prescribed. The sun bends the path inward, but the bending angle depends on speed. Faster objects are deflected less. Because 3I/Atlas arrives with substantial inbound velocity, the expected deflection is modest. Passive dynamics therefore predict a shallow turn rather than a dramatic swing. This expectation is encoded in the initial orbital solution and serves as a reference. Planetary perturbations add complexity but remain passive. As the object passes through the solar system, it experiences small gravitational tugs from planets. These tugs can slightly alter the path, changing the exact orientation of the outbound leg. The magnitude of these effects depends on distance. Close encounters can produce large changes, while distant passes produce negligible ones. For 3I/Atlas, the entry geometry keeps it far from close planetary approaches, so expected perturbations are small and calculable. Under passive dynamics, the object's rotation does not influence its orbit. Spin affects how the object presents its surface to light and heat, but does not change its center of mass motion. Similarly, shape irregularities do not matter unless they interact with forces beyond gravity. In the passive model, the object can be spherical or elongated, rotating or tumbling without altering the predicted path. Radiation from the sun is also ignored at this stage. Light carries momentum and can exert pressure, but for most small bodies this effect is tiny compared to gravity, especially at moderate distances. Passive dynamics assume that such effects are negligible. This assumption is valid for many asteroids and comets when they are inactive. It simplifies the model and allows deviations to stand out clearly when they occur. The passive framework also assumes no mass loss. If the object sheds material, the ejection of mass can produce a reaction force altering motion. In passive dynamics, the object retains constant mass. This assumption again holds for inert bodies and inactive comets. It defines a clean baseline against which any thrust-like behavior can be measured. Predictions generated under this framework are precise. Given the initial conditions, astronomers can compute where the object should appear in the sky at any future time. These predictions include expected positions, velocities, and timing. They also include uncertainties derived from measurement error. If subsequent observations fall within these uncertainties, the passive model is considered adequate. The usefulness of this baseline lies in its rigidity. Passive dynamics leave little room for adjustment. Gravity is well understood, and its effects are calculable to high precision. As a result, any systematic deviation between prediction and observation suggests the presence of additional forces. Random scatter can be attributed to noise. Persistent offsets that grow over time cannot. In practice, astronomers compute a best fit gravitational orbit and then examine residuals. Residuals are the differences between observed positions and those predicted by the model. In a purely passive case, residuals should be small and randomly distributed around zero. They should not show trends with time or distance. This statistical behavior is expected and tested routinely for asteroids and comets. For an interstellar object, passive expectations also include stability of excess velocity. The inbound and outbound speeds far from the Sun should match within error. Any change would indicate energy exchange. Under gravity alone, no such exchange occurs. Energy is conserved. This conservation provides another check on the model. The passive description does not deny the possibility of additional forces, it simply postpones them. By first establishing what should happen if nothing unusual occurs, the analysis creates a clear contrast. This method avoids confusion. Without a baseline, it would be difficult to tell whether observed behavior is normal or exceptional. It is important that the passive model is applied uniformly. The same assumptions are used for all objects unless evidence suggests otherwise. This consistency prevents bias. An object is not treated as special until data demand it. For 3I/Atlas, the passive dynamics are calculated and accepted provisionally just as they would be for any newly discovered body. As observations accumulate, the passive predictions are updated with refined initial conditions. This improves accuracy, but does not change the underlying expectations. The symmetry of the path, the conservation of energy, and the absence of non-gravitational forces remain central. These features define what it means for the object to behave like an inert body moving under gravity alone. The region of expected passive dynamics concludes with a complete gravitational description of motion. It provides predicted positions and velocities across the observed interval and beyond. It specifies how the object should accelerate and decelerate, how its path should curve, and how it should emerge after perihelion. This description is not speculative. It is grounded in mechanics tested across centuries and confirmed in countless observations. By establishing this baseline, the analysis prepares to examine whether 3I/Atlas conforms to these expectations. Any departure must be measured against this passive framework. The question is not whether the model is elegant or familiar, but whether it matches reality. The answer emerges only through comparison, which belongs to the next stage of inquiry. Against the predictions set by passive dynamics, the observed motion of 3I/Atlas begins to show small but persistent deviations. These deviations are not dramatic shifts or sudden changes. They are subtle differences that accumulate over time, detectable only through careful comparison between predicted and measured positions. In early observations, residuals appear within expected uncertainty, but as the observational arc lengthens, a pattern emerges. The object is consistently offset from its purely gravitational track by an amount that cannot be fully explained by measurement noise alone. The offsets are directional rather than random, indicating a systematic influence. This pattern becomes clearer as additional data are gathered across days and weeks. Each new observation, when compared to the passive model, reinforces the same small discrepancy. The effect is modest in magnitude, far smaller than the gravitational influence of a planet, yet large enough to matter, given the precision of modern astrometry. The deviations manifest primarily along the direction of motion, altering the timing of the object's arrival at predicted sky positions rather than displacing it strongly sideways. This timing shift suggests a slight change in speed relative to the passive expectation. When the object is inbound, it arrives marginally earlier than predicted. When outbound, it departs slightly faster than the model allows. The symmetry expected of a purely gravitational hyperbolic path is therefore imperfect. Energy appears not to be strictly conserved within the passive framework, though the difference is small. These observations prompt recalculation of the orbit under the assumption of gravity alone, adjusting initial conditions to see whether a better fit can be achieved. Despite these adjustments, residuals persist. The best fit gravitational solution reduces but does not eliminate the systematic offsets. The remaining discrepancies grow with time, indicating that they are not artifacts of an incorrect starting point, but reflect an ongoing influence acting on the object. The magnitude of the deviation corresponds to an acceleration far weaker than solar gravity, yet sustained over a significant portion of the trajectory. This acceleration is measurable because the object's path is otherwise simple and well constrained. The fact that the deviations increase closer to the Sun suggests a relationship with solar distance. When the object is far away, residuals are minimal. As it approaches, the divergence from the passive model becomes more pronounced. This distance dependence narrows the range of possible explanations. Random measurement error does not depend on solar distance. Gravitational perturbations from distant planets are already included in the model and remain too small to account for the effect. The deviations also do not correlate with Earth's position or viewing geometry, which would suggest observational bias. Instead, they track the object's own position along its path. Astronomers examine whether unmodelled gravitational influences could be responsible. The mass distribution of the solar system is well known, and no unseen massive body lies along the object's trajectory. The possibility of a close approach to an unrecognised small body is considered and dismissed due to the lack of sudden changes or directional shifts that such an encounter would produce. The deviation is smooth and continuous, inconsistent with impulsive events. Attention then turns to the statistical robustness of the signal. Independent teams using different data sets and reduction methods report similar residual patterns. This convergence reduces the likelihood that the effect arises from a specific instrument or processing pipeline. The deviations remain when subsets of the data are analysed separately, indicating that no single observation dominates the result. The acceleration inferred from these deviations is small but coherent, acting over weeks rather than moments. Its direction aligns approximately with the line from the object to the Sun, suggesting a radial component. This orientation is important because many known non-gravitational effects act in this direction. However, at this stage, the analysis remains descriptive. The data show that the object does not follow the passive gravitational path exactly. The difference is measurable, repeatable, and correlated with solar distance. The magnitude of the effect is comparable to non-gravitational accelerations observed in some comets, though no visible activity is detected. This comparison is noted cautiously without implying cause. The absence of a visible coma or tail remains a constraint. If material is being released, it must be in a form that does not produce detectable dust or gas clouds at the observed distances and sensitivities. The observed deviations also differ in detail from those of typical active comets. In many comets, non-gravitational forces vary strongly with rotation and show complex temporal behavior. For 3I/Atlas, the deviations appear smoother, lacking abrupt changes that would indicate episodic activity. This smoothness suggests a relatively steady influence rather than bursts. The analysis also checks for correlations with brightness variations that might indicate rotation coupled to force modulation. While minor brightness changes are present consistent with rotation, they do not map cleanly onto the timing of the deviations. This weakens a direct rotational explanation, but does not exclude it. Throughout this examination, caution remains central. The deviations are small enough that overinterpretation would be easy. Astronomers therefore limit conclusions to what the data require. What is required is acknowledgement that gravity alone does not fully describe the observed motion. The passive model, while accurate in broad terms, leaves systematic residuals that point to an additional effect. The data do not specify the nature of this effect. They define its magnitude, direction, and dependence on distance, but not its physical origin. This restraint is deliberate. By separating observation from explanation, the analysis preserves clarity. The observed deviations stand as an empirical fact independent of any particular mechanism. They mark the transition from purely geometric and gravitational description to consideration of other forces that can act on small bodies in space. The existence of these deviations does not imply intent or control. It indicates response. The object reacts to its environment in a way that alters its motion slightly but measurably. This reaction is the next layer of inquiry. For now, the record shows that 3I/Atlas does not behave exactly like an inert object moving under gravity alone. It follows its predicted path closely, yet not perfectly, leaving a narrow but persistent gap between expectation and observation. With deviations from passive dynamics established, the next region of inquiry focuses on measurement verification. This stage does not seek new explanations, but tests whether the observed discrepancies could arise from error bias or limitation in the data itself. The goal is to determine whether the deviations are intrinsic to the object's motion or artifacts of observation and analysis. This process is methodical and conservative, reflecting the understanding that extraordinary interpretations are unnecessary if ordinary errors suffice. Astrometric measurements begin as light recorded by detectors. Each recorded position depends on calibration of the instrument, timing accuracy, atmospheric conditions, and data reduction procedures. Any systematic flaw in these elements could shift measured positions in a consistent way. To assess this, astronomers examine the full chain from photon arrival to reported coordinates. Calibration frames taken before and after observations are reviewed to ensure detector geometry and sensitivity are stable. Timing systems are checked against known standards to confirm that recorded observation times are accurate to within the required precision. Atmospheric effects are a primary concern for ground-based observations. Turbulence can blur images and shift apparent positions. Refraction bends light as it passes through air, altering apparent positions depending on altitude above the horizon. These effects are well characterized and corrected using established models. For 3I/Atlas, observations span a range of altitudes and atmospheric conditions. If atmospheric correction were responsible for the deviations, residuals would correlate with viewing angle or weather. Analysis shows no such correlation, Residuals persist across different nights, elevations and conditions, suggesting that atmosphere-related errors are not the cause. Instrumental bias is another possibility. A misaligned camera or a subtle distortion in the optical system could introduce systematic offsets. To test this, measurements of the object are compared against measurements of background stars in the same frames. These stars serve as fixed reference points. If the instrument introduced a bias, it would affect all sources similarly. The background stars, however, show no comparable systematic shifts. Their positions remain consistent with catalogue values within expected uncertainty. This differential stability indicates that the instrument performs as intended. Data reduction pipelines are also scrutinized. Automated software identifies sources, matches them to catalogues, and computes positions. Different pipelines may use different algorithms and assumptions. To test robustness, independent teams process the same raw data using separate methods. For 3i/Atlas, these independent reductions produce consistent astrometric results. The deviations from the passive model appear regardless of the specific pipeline used. This convergence reduces the likelihood that software choices drive the effect. Cross-observatory comparison provides an additional check. Observations come from multiple facilities with different instruments, detectors, and calibration procedures. If a deviation were due to a specific telescope or site, it would not appear consistently across all datasets. In this case, measurements from different observatories agree within their respective uncertainties and show similar residual patterns when compared to the passive model. This consistency across independent systems strengthens confidence in the reality of the observed effect. The role of reference star catalogues is also examined. Astrometric positions rely on catalogues that provide accurate locations of background stars. Errors or biases in these catalogues could propagate into object positions. Modern catalogues are constructed using space-based observations and have well-quantified uncertainties. Any catalogue bias would affect all measurements tied to it in a similar way. Analysis shows that residuals for 3i/Atlas do not align with known catalogue systematics. Moreover, different catalogues yield similar results. Timing accuracy is critical when measuring motion. An error of even a fraction of a second can shift predicted positions for fast-moving objects. Timing systems are therefore cross-checked against atomic standards. Logs show no anomalies. Additionally, timing errors would produce shifts along the direction of motion, but would not vary with solar distance in the observed manner. The distance-dependent nature of the deviations argues against simple timing faults. Photometric effects are also considered. The apparent position of a source can be influenced by its brightness distribution. If the object's light were asymmetric due to unresolved activity, the centroid might shift slightly. This effect is known in comets with extended comae. For 3i/Atlas images show a point-like source with no detectable extension. Any asymmetry would have to be extremely subtle. Simulations of such effects indicate that they would produce random or rotation-dependent shifts rather than the smooth radial acceleration observed. Statistical analysis of residuals provides another layer of verification. Residuals are plotted as a function of time distance and observational parameters. Random errors produce scatter without trend. Systematic errors tied to specific conditions produce recognizable patterns. The residuals for 3i/Atlas show a coherent trend with solar distance increasing in magnitude as the object approaches the Sun. This behavior is inconsistent with known observational biases, which depend more strongly on viewing geometry or instrument state. The possibility of selection bias is also addressed. Because observers may focus more attention on unusual objects, data coverage could be uneven, potentially skewing analysis. In this case, the deviations appear even when using evenly sampled subsets of the data. Removing specific nights or observatories does not eliminate the effect. The result is not driven by a small portion of the dataset. Numerical methods used in orbit fitting are tested as well. Different integration schemes and fitting algorithms can yield slightly different solutions, especially for short arcs. Multiple methods are applied, including those optimized for small body dynamics, and those used routinely for asteroids and comets. All methods converge on similar residuals when constrained to gravity alone. Introducing additional parameters improves the fit, indicating that the passive model is incomplete rather than misapplied. Throughout this verification process, the guiding principle is elimination. Each potential source of error is considered and tested against the data. Those that fail to reproduce the observed pattern are set aside. What remains is the conclusion that the deviations are not artifacts of measurement or analysis. They represent a genuine difference between predicted and observed motion. This conclusion is not framed as certainty beyond doubt. Instead, it is framed as robustness. Given the available data, no plausible combination of known errors accounts for the effect. The deviations persist across instruments, methods, and conditions. They scale with distance in a physically meaningful way. They align in direction with the sun-object line. These properties collectively indicate that the effect arises from the object's interaction with its environment rather than from observational shortcomings. By completing this verification layer, the analysis clears a necessary threshold. Only after measurement error is ruled out can additional forces be considered seriously. This step protects against misinterpretation and ensures that subsequent explanations address a real phenomenon. The object's motion differs slightly but consistently from passive expectations, and this difference survives rigorous scrutiny. The outcome of this region is therefore a confirmation rather than a discovery. It confirms that the deviations identified earlier are intrinsic to the object's trajectory. With this assurance, analysis can move inward from the reliability of measurement to the physical processes capable of producing the observed acceleration. With measurement reliability established, attention turns to physical mechanisms capable of producing the observed deviations. At this stage, the analysis shifts from elimination to modelling. The task is not to propose exotic explanations prematurely, but to evaluate known forces that act on small bodies in interplanetary space, and determine whether any can account for the magnitude, direction, and distance dependence of the acceleration. Each candidate mechanism is assessed against three constraints: consistency, with the data compatibility with observed physical properties, and plausibility within established physics. Gravitational perturbations from known bodies are the first consideration. In principle, an unmodelled gravitational influence could alter the trajectory. All major planets are already included in the dynamical model, as are relativistic corrections and the effects of large asteroids where relevant. The remaining possibility would be an unknown massive body, or a close encounter with a small object. An unseen massive body would have to exert a measurable influence not only on 3I/Atlas, but on other objects as well. No such correlated anomalies are observed. A close encounter with a small body would produce a localized deflection rather than a smooth continuous acceleration that scales with solar distance. The observed deviations do not exhibit the temporal signature of an encounter. Gravitational explanations therefore fail to match the data. Radiation pressure is the next mechanism considered. Photons emitted by the sun carry momentum and exert a force when they strike an object. This force acts radially outward and decreases with the square of distance from the sun matching the direction and scaling of the observed acceleration. Radiation pressure has been measured and modelled extensively, particularly for small and low-mass objects. To evaluate its relevance here, one must consider the object's area-to-mass ratio. For a compact rocky body of typical asteroid density, radiation pressure produces an acceleration far too small to account for the observed effect. To match the data, the object would need an extremely low mass relative to its cross-sectional area. Such a requirement leads to consideration of unusual shapes or structures. A thin sheet-like object would experience a much stronger acceleration from radiation pressure. However, photometric observations of 3I/Atlas show brightness variations consistent with a modest aspect ratio, not an extreme one. There is no evidence for the kind of rapid high-amplitude light curve expected from a tumbling ultra-thin structure. Additionally, survival of such a structure through interstellar space and solar approach raises stability concerns. While radiation pressure cannot be dismissed outright, it requires assumptions that strain observational constraints. Outgassing is a more familiar mechanism. Comets experience non-gravitational acceleration due to the sublimation of volatile ices, which produces jets of gas and dust. These jets act like thrusters altering the orbit. The acceleration typically increases as the object approaches the Sun and decreases as it recedes, broadly consistent with the observed distance dependence. For known comets, outgassing is accompanied by visible Comean tails. 3I/Atlas, however, shows no detectable coma or tail within observational limits. This absence complicates but does not automatically exclude outgassing. One possibility is that the outgassing involves volatiles that do not produce easily detectable dust or optical signatures. Gases such as molecular hydrogen, nitrogen, or carbon monoxide can sublimate at low temperatures and may escape without dragging significant dust. Such activity could generate thrust while remaining visually subtle. Models of hydrogen outgassing in particular have been proposed for other anomalous objects. To test this, one examines whether the required gas production rate is physically reasonable. Calculations show that a modest mass loss rate well below that of typical comets could generate the observed acceleration if the gas is expelled anisotropically. The total mass loss over the observed arc would be small enough to evade direct detection. However, this explanation introduces its own challenges. Sustaining anisotropic outgassing requires either localized active regions or a thermal gradient that persists over time. The object would also need to retain sufficient volatile material despite exposure to interstellar radiation over long timescales. While not impossible, these conditions require careful justification. Observationally, searches for gas emission lines provide constraints. To date, no definitive detection has been reported, but upper limits remain compatible with the low production rates required by the model. Thermal forces unrelated to mass loss are also considered. The Yarkovsky effect arises from anisotropic thermal emission, as an object absorbs sunlight and re-emits energy as heat. This effect can alter asteroid orbits over long time scales. For small near-Earth asteroids, it is measurable. The magnitude of the Yarkovsky acceleration depends on rotation state thermal properties and size. For 3I/Atlas, estimates indicate that the Yarkovsky effect is orders of magnitude too small to explain the observed deviations. Additionally, its direction depends on rotation, not purely radial, making it a poor match to the data. Solar wind pressure is another candidate. Charged particles emitted by the Sun exert pressure on objects in space. This force is generally much weaker than radiation pressure and highly variable. It also depends on magnetic and electrical properties of the object. Even under optimistic assumptions, solar wind pressure cannot account for the measured acceleration. Its variability would also introduce noise rather than the smooth trend observed. Electrostatic forces have been proposed in some contexts, particularly for dust grains. Charging by solar ultraviolet radiation could in principle lead to interactions with the solar magnetic field. For macroscopic bodies, these effects are negligible. The charge-to-mass ratio required to produce the observed acceleration would be unrealistically high. This mechanism can be excluded. At this point, the viable mechanisms narrow to two broad classes: radiation pressure acting on an object with an unusually high area to mass ratio and low-level outgassing of volatile material without a visible coma. Both are consistent with the radial direction of the acceleration and its dependence on solar distance. Distinguishing between them requires deeper consideration of physical plausibility and consistency with all observations. Radiation pressure models require the object to be either extremely porous, very thin, or composed of low-density material. Such properties might arise from a fractal aggregate or a fluffy structure. However, survival through interstellar space and passage through the inner solar system would tend to compact or disrupt such structures. Additionally, the lack of extreme photometric variability argues against a highly anisotropic shape. Outgassing models, while invoking unseen activity, align more closely with known behavior of small bodies. The absence of dust does not preclude gas-driven thrust. The required mass loss rates are modest, and the thermal environment near the Sun provides a natural energy source. The main uncertainty lies in the nature and retention of the volatiles. If the object formed in a cold environment and spent most of its history in interstellar space, it could plausibly preserve such materials beneath an insulating layer. Crucially, introducing an outgassing term into the dynamical model improves the fit significantly. Residuals are reduced and the remaining scatter is consistent with measurement noise. Radiation pressure models can also improve the fit, but only under extreme parameter choices. From a modelling perspective, outgassing provides a more flexible and less constrained explanation. The role of parsimony is important here. The analysis does not claim to identify the definitive mechanism, but it weighs explanatory economy. Known cometary physics extended to an unusual but not unprecedented regime requires fewer assumptions than invoking a fundamentally novel structure. This does not render alternative explanations invalid, but it assigns them lower prior plausibility given current evidence, therefore concludes with a provisional assessment. The observed non-gravitational acceleration is real and solar-directed. Among known physical mechanisms, subtle outgassing of volatile material provides the most consistent explanation, while radiation pressure remains a secondary possibility, requiring atypical properties. Other forces can be excluded. This conclusion sets the stage for the next layer of analysis, which examines what these mechanisms imply about the object's origin, composition, and classification. With candidate mechanisms identified, the analysis now turns to implications. This stage asks not what force acts on the object, but what that force reveals about the object itself. Physical behavior constrains origin structure and evolutionary history. By tracing these constraints carefully, one can situate 3I/Atlas within a broader taxonomy of small bodies while acknowledging the limits of inference. The aim is not classification by resemblance alone, but classification by necessity, what must be true for the observed behavior to occur. If subtle outgassing is responsible for the acceleration, the object must contain volatile material capable of sublimating under solar heating. This immediately distinguishes it from inert rocky asteroids formed deep within warm protoplanetary disks. Volatiles such as carbon monoxide, nitrogen, or molecular hydrogen condense only at very low temperatures. Their presence implies formation in a cold environment, either in the outer regions of a planetary system or within a dense molecular cloud prior to star formation. This is consistent with an interstellar origin, where objects may be ejected early and spend most of their existence far from stellar heating. Retention of volatiles over long timescales presents a challenge. Interstellar space is cold, but it is not benign. Cosmic rays and background radiation slowly erode exposed ices. For an object to retain sublimation-capable material over millions or billions of years, those volatiles must be shielded. This implies either burial beneath an insulating mantle or incorporation within a matrix that limits diffusion. Models of cometary evolution show that a refractory crust can form naturally, as more volatile components sublimate away, leaving behind a protective layer. Such a structure could preserve deeper volatiles until renewed heating occurs during stellar approach. The absence of a visible coma suggests that if outgassing is present, it is gas-dominated rather than dust-dominated. Dust production depends on the coupling between gas flow and solid grains. If the surface material is cohesive or the gas production rate is low, dust may not be lifted efficiently. Alternatively, the object may be depleted in fine dust due to prior processing. Interstellar travel could preferentially strip loosely bound particles, leaving behind a compact surface that releases gas but little particulate matter. This scenario aligns with both the lack of optical activity and the presence of dynamical acceleration. Anisotropy is a critical requirement. Outgassing must be directional to produce net thrust. This implies either localized active regions or a persistent thermal gradient. Rotation complicates this picture. A rapidly rotating body would average out directional forces unless activity is strongly localized or tied to subsurface structure. Light curve observations provide some constraints on rotation period and amplitude. The absence of extreme variability suggests moderate rotation and shape. This does not preclude anisotropic outgassing, but suggests that the active regions are either small or thermally decoupled from the bulk rotation. If radiation pressure is instead responsible, the implications are more radical. The object would need an unusually high area to mass ratio. This could arise from extreme porosity, such as a fractal aggregate with very low bulk density. Laboratory and numerical studies show that such aggregates can form in protoplanetary disks. However, their mechanical strength is low. Survival through ejection from a planetary system, interstellar transit and solar encounter would require resilience against tidal forces, collisions with dust and thermal stresses. While not impossible, this survival pathway is narrow. Porous structures also have distinctive thermal properties. They heat and cool rapidly and may exhibit strong temperature gradients. This could influence both radiation pressure response and any residual outgassing. Observationally, such properties might manifest as unusual thermal emission signatures. Infrared observations could therefore discriminate between dense and porous structures. To date, available data do not show anomalies strong enough to demand extreme porosity, though sensitivity limits leave room for ambiguity. Origin scenarios follow naturally from these structural considerations. An outgassing-dominated interpretation suggests that 3I/Atlas is an interstellar comet, albeit an atypical one. It would differ from classical comets primarily in scale and activity level rather than in kind. Its behavior would reflect both its formative environment and its long isolation from stellar heating. This interpretation places the object within an emerging population of interstellar debris that spans a continuum from inactive rocky bodies to visibly active comets. A radiation pressure interpretation, by contrast, pushes the object toward the edge of known natural categories. While still potentially natural, it would represent an extreme end member. This raises questions about frequency. If such objects exist, how common are they? Detection bias strongly favors objects with large area to mass ratios, because they respond more strongly to non-gravitational forces and may be easier to detect. The fact that few such objects have been observed suggests either rarity or observational incompleteness. The former would argue against this being a typical representative of interstellar debris. Classification is therefore probabilistic rather than absolute. The object shares some properties with comets, some with asteroids, and some with neither cleanly. The key distinction lies not in appearance but in dynamics. Its motion indicates active interaction with solar radiation or heating. This places it outside the category of purely inert bodies. At the same time, the lack of visible activity challenges traditional comet definitions. The object occupies an intermediate regime, highlighting the limitations of binary classification schemes. This ambiguity is scientifically productive. It forces refinement of categories and models. The solar system already contains examples of objects that blur boundaries, such as active asteroids and dormant comets. Interstellar objects add another dimension, sampling formation environments beyond the Sun's influence. 3I/Atlas thus serves as a probe not only of its own nature, but of the diversity of small body formation processes in the galaxy. Temporal evolution provides another lens. As the object continues along its trajectory, changes in acceleration or activity could reveal underlying mechanisms. An increase in acceleration with decreasing distance followed by a decline post-perihelion would support a thermally driven process. A constant acceleration scaling strictly with inverse square distance would favor radiation pressure. Monitoring over time is therefore critical. Predictions diverge, allowing future data to refine or overturn current interpretations. The object's past is also constrained by its present behavior. If volatiles are responsible, they must have survived ejection from the parent system. This suggests relatively gentle ejection processes or rapid burial after formation. Violent scattering events could heat and devolatilize material. Therefore, the object may originate from a region where dynamical interactions are less destructive, such as the outer disk or a young system with abundant gas damping. This insight feeds back into models of planet formation and debris ejection across stellar systems. Importantly, none of these implications require invoking artificial origin or unknown physics. The analysis remains grounded in extensions of known processes into unfamiliar regimes. This restraint is intentional. The role of this section is not to speculate beyond evidence, but to trace logical consequences. Extraordinary claims demand extraordinary evidence, and no such evidence is present here. What is present is a reminder that natural diversity can be surprising without being inexplicable. Section 10 therefore synthesizes behavior and implication. The object's non-gravitational acceleration constrains its composition to include either volatiles or extreme structural properties. Among these, volatile-driven activity fits more comfortably within known astrophysical processes. This points toward an interstellar cometary nature, albeit one with low activity and unusual presentation. The object challenges simple labels but enriches understanding by doing so. Having established these implications, the analysis is prepared to move outward again from the object to the broader population. The final stage will ask what 3I/Atlas implies statistically and conceptually about interstellar objects as a class, and how future detections may refine or revise the picture formed here. With the object's physical implications outlined, the analysis widens its scope to population-level meaning. Individual anomalies are informative, but their greatest value lies in what they reveal about underlying distributions. 3I/Atlas is not interpreted in isolation, but as a data point within a sparse and biased sample of interstellar visitors. This section examines what can and cannot be inferred from that sample, how detection biases shape interpretation, and how this object alters expectations about the frequency, diversity, and nature of extrasolar small bodies. Interstellar objects are detected only when they pass close enough to the Sun to become visible, and when their trajectories and brightness intersect the limits of current surveys. This immediately imposes a strong selection effect. Objects with higher intrinsic brightness, unusual dynamics or non-gravitational acceleration are easier to notice and track. Inert, dark, fast-moving bodies may pass undetected. Therefore, the known sample is almost certainly unrepresentative. Any attempt to generalize must account for this observational filter. 3I/Atlas exhibits non-gravitational acceleration that increases its detectability. Deviations from predicted motion draw attention and prompt follow-up. This does not imply that such deviations are common among interstellar objects, only that they are more likely to be noticed when present. Conversely, objects behaving exactly as expected under gravity may blend into the background of asteroidal detections until after they have passed. The sample is therefore weighted toward dynamical oddities. Despite this bias, the presence of even one object exhibiting subtle activity without obvious visual signatures expands the conceptual space of what interstellar debris can look like. Prior expectations often divided such objects into two rough categories: comet-like bodies with obvious activity and asteroid-like bodies that are inert. 3I/Atlas occupies an intermediate regime. Its behavior suggests that low-level activity may be common but difficult to detect directly. If so, The apparent rarity of active interstellar objects may be an artifact of sensitivity rather than true scarcity. Population models of interstellar debris depend critically on ejection mechanisms. Planetary systems are thought to eject vast numbers of small bodies during formation and evolution. Giant planet migration, close encounters, and stellar flybys all contribute. These processes operate across a range of temperatures and compositions. If ejection predominantly samples outer colder regions, then volatile-rich bodies should be abundant. If inner regions dominate, rocky inert bodies should prevail. The observed mix provides constraints. 3I/Atlas supports the idea that volatile-bearing objects survive ejection and long-term interstellar travel more often than previously assumed. Its subtle activity suggests that volatiles need not be exhausted or destroyed. This shifts population expectations toward a higher fraction of objects capable of responding dynamically to stellar heating. Importantly, this does not require them to resemble classical comets. Many may remain visually inactive while still dynamically active. The mass and size distribution of interstellar objects is another open question. Surveys are biased toward detecting larger and brighter objects. If small objects dominate numerically as expected from collisional cascades, then most interstellar debris passes unnoticed. Non-gravitational acceleration effects scale inversely, with mass making smaller objects more susceptible. Therefore, among detected objects, those with measurable acceleration may preferentially be small. 3I/Atlas fits this pattern. This suggests that the detected sample is doubly biased towards small objects and toward those with active or low-density properties. Statistical inference from such a sample must be cautious. One cannot infer typicality from detectability, however one can infer possibility. The existence of this object demonstrates that interstellar debris can preserve volatiles, exhibit subtle activity and survive transit. Any comprehensive model of interstellar populations must accommodate this. Models that predict rapid devolatilization or structural collapse for all small bodies are disfavored. There are also implications for survey strategy. If subtle non-gravitational effects are common, then precise astrometry becomes a primary diagnostic tool. Visual classification alone is insufficient. Objects previously classified as inert interstellar asteroids may warrant reanalysis with non-gravitational models. Conversely, future surveys designed with higher cadence and precision could identify acceleration signatures, earlier improving characterization. The role of cadence is particularly important. Non-gravitational acceleration reveals itself over time. Sparse observations may mask it. 3I/Atlas benefited from sustained tracking. As survey coverage improves, the fraction of detected objects showing such effects may increase. This would not necessarily indicate a change in the population, only improved sensitivity. Another population-level implication concerns diversity. Interstellar space aggregates debris from countless systems with varying architectures and histories. Diversity should therefore be high. The temptation to interpret the first few detections as representative must be resisted. Instead, each object should be treated as a boundary marker outlining the envelope of what exists. 3I/Atlas expands that envelope toward low-activity, dynamically responsive bodies. This perspective reframes debates about anomaly, anomalous relative to what relative to solar system expectations shaped by limited local sampling. When the frame of reference expands to galactic scales, variance increases. Behaviors that appear unusual locally may be common globally. The appropriate scientific response is not surprise but recalibration. The object also informs estimates of interstellar object density. Density estimates rely on detection rates and assumed size distributions. If detectability is enhanced by non-gravitational acceleration, then inferred densities based on observed counts may be biased high. Correcting for this requires modelling how many objects pass undetected because they lack such signatures. 3I/Atlas therefore adds complexity to population estimates rather than clarity. But this complexity reflects reality rather than error. Importantly, none of these implications require that interstellar objects be rare curiosities. On the contrary, models suggest they are abundant. What is rare is detection. As instrumentation improves, the transition from anecdotal to statistical science will occur. 3I/Atlas belongs to the anecdotal era, but contributes meaningfully by highlighting which parameters matter most. Conceptually, the object underscores the continuity between solar system small bodies and interstellar ones. Differences are of degree, not kind. The same physical processes apply: sublimation, radiation, pressure, thermal effects, and gravity. What differs is history and environment. Interstellar objects sample conditions not preserved locally. They act as messengers carrying integrated information about formation and evolution elsewhere. This perspective tempers speculative narratives. When confronted with unusual behavior, it is tempting to invoke extraordinary origins. However, population reasoning favors mundane explanations extended across vast numbers. Given enough systems and enough time, rare combinations of properties become inevitable. 3I/Atlas does not demand a new category of physics or origin. It exemplifies the tale of a natural distribution. Section 11 thus situates the object within a broader statistical and conceptual framework. It neither overstates its representativeness nor dismisses its significance. The object is important precisely because it reveals how little is needed to stretch expectations. Subtle activity, preserved volatiles, and non-gravitational motion may be common features of interstellar debris, even if rarely observed. The analysis is now complete in its outward expansion. The final section will close the loop by integrating dynamics, physics, and population context into a coherent conclusion, clarifying what is known, what remains uncertain, and what 3I/Atlas ultimately teaches about the universe through which it passes. The analysis now closes by integrating the threads developed across preceding sections into a coherent synthesis. The objective of this final section is not to restate conclusions mechanically, but to clarify their logical structure, delimit their scope, and articulate what has genuinely been learned. Throughout this work, restraint has been as important as inference. Each step has been governed by the principle that interpretation must remain anchored to evidence, and that uncertainty, when unavoidable, must be explicitly preserved rather than obscured. The starting point was dynamical anomaly. Observations showed that the trajectory of 3I/Atlas deviates slightly but consistently from the expectations of a purely gravitational model. This deviation is small in absolute terms, yet statistically significant and persistent across independent datasets. Importantly, it is directional, approximately radial, with respect to the Sun, and scales with solar distance in a smooth and physically interpretable way. These features distinguish it from noise error or transient perturbation. The anomaly is not dramatic, but it is real. From there, the analysis moved deliberately through verification, measurement error, instrumental bias, atmospheric effects, timing inaccuracies, catalogue systematics, and numerical artifacts were each examined and tested. None could reproduce the observed pattern. The deviation survived cross-observatory comparison, independent data reduction, and alternative orbital fitting methods. This stage did not claim infallibility, but it established robustness. The effect cannot be reasonably attributed to known observational shortcomings. Only after that threshold was crossed were physical mechanisms considered. Known forces acting on small bodies were evaluated against the constraints imposed by the data. Gravitational explanations were excluded due to their inability to produce a smooth, solar-directed acceleration. Thermal recoil effects such as Yarkovsky were found to be far too weak. Solar wind and electrostatic forces failed on both magnitude and stability grounds. This narrowing process left two viable classes of explanation: radiation pressure, acting on an object with an unusually high area to mass ratio and low-level outgassing of volatile material without an accompanying visible coma. Each of these mechanisms was examined not in isolation but in relation to observational constraints. Radiation pressure offers an elegant scaling law, but requires extreme structural properties that strain plausibility and lack supporting evidence. Outgassing, while invoking unseen activity, aligns more naturally with known physics extended into a low-activity regime. The absence of dust does not invalidate this explanation. Gas-dominated sublimation at modest rates is consistent with both the dynamical signal and the lack of optical features. Introducing such a force into the dynamical model improves the fit substantially, without resorting to extreme assumptions. From mechanism, the analysis proceeded to implication. If outgassing is responsible, then 3I/Atlas must contain volatiles preserved from a cold formation environment and shielded over long timescales. This points toward an interstellar origin, consistent with formation in outer disk regions or similarly cold settings. The object would not be a classical comet, but neither would it be inert. It would occupy an intermediate regime that already exists within the solar system, but is amplified by the diversity of extrasolar formation pathways. If radiation pressure were responsible, the object would represent an extreme structural outlier. While not impossible, this interpretation requires a convergence of properties that appear less supported by current data. The analysis, therefore, assigns it lower plausibility without excluding it entirely. Crucially, neither explanation requires new physics, artificial origin, or speculative constructs. Known processes suffice. This conclusion is not an argument from conservatism, but from sufficiency. There is no explanatory gap demanding more radical hypotheses. The population-level perspective then contextualized the object's significance. Interstellar detections are subject to severe selection effects. Objects that behave oddly are more likely to be noticed, tracked, and studied. 3I/Atlas is therefore not necessarily typical, but it is informative. It expands the envelope of known behavior and demonstrates that subtle, dynamically active interstellar objects can exist without dramatic visual signatures. This insight forces a recalibration of expectations rather than a revision of fundamentals. One of the most important lessons is methodological. The analysis illustrates how small deviations, when treated seriously but cautiously, can yield meaningful insight. It also shows the danger of overinterpretation. The object's behavior is unusual, but unusual does not mean inexplicable. In astrophysics, where sample sizes are small and distance is vast, the tail of a distribution often appears before its center. Recognizing this prevents both complacency and sensationalism. Another lesson concerns classification. Traditional labels such as asteroid and comet are insufficient when applied rigidly, especially to interstellar objects. These categories were developed based on local populations shaped by the Sun's formation environment. When sampling debris from across the galaxy, continuity rather than discreteness should be expected. 3I/Atlas exemplifies this continuity. Its behavior is comet-like in dynamics, asteroid-like in appearance, and interstellar in origin. None of these descriptors alone is adequate. The analysis also underscores the value of precision astrometry. Subtle forces reveal themselves not through dramatic displays, but through cumulative deviation. As surveys improve in cadence, sensitivity, and duration, the ability to detect and interpret such deviations will increase. Future interstellar detections may reveal that non-gravitational effects are common, even if visually undetectable. This will shift emphasis from appearance to motion as the primary diagnostic. Equally important is what the analysis does not claim. It does not assert certainty regarding the specific volatile involved, the internal structure of the object, or its exact formation history. It does not claim representativeness of the broader population. It does not claim novelty beyond natural diversity. These absences are not weaknesses but reflections of disciplined inference. Scientific understanding advances not by eliminating uncertainty, but by bounding it. In sum 3I/Atlas teaches a modest but durable lesson. Interstellar objects need not conform to familiar archetypes. They may carry volatiles without spectacle, respond to solar heating without obvious activity, and deviate from passive motion without invoking exotic causes. Their study rewards patience, precision, and restraint. The object passes through the solar system, briefly leaving behind not a mystery, but a refinement. It refines expectations about what extrasolar debris can be, how it behaves, and how it should be studied. In doing so, it affirms a broader principle of astronomy. The universe is not obligated to align with our categories, only with its own laws. When those laws are applied carefully, even the unfamiliar becomes intelligible. Having reached synthesis, the analysis now extends one final step, not to add conclusions, but to project consequences. This section addresses what follows logically from the work already done: how future observations should be designed, how interpretation frameworks must adapt, and how the case of 3I/Atlas reshapes the practice of studying rare transient phenomena. This is not speculation about the object itself, but about the discipline that encounters it. The first consequence concerns observational priority. Historically, interstellar objects have been treated as curiosities until proven otherwise. Follow-up resources are often limited, delayed, or narrowly focused on appearance rather than motion. The case examined here demonstrates that the most diagnostically rich information may reside in subtle dynamical behavior rather than spectacular morphology. This implies a shift in emphasis. Rapid high-precision astrometric monitoring should be treated as essential rather than supplementary. The sooner non-gravitational signatures are identified, the more effectively models can be constrained. This shift has practical implications for survey design. Wide-field surveys optimized for discovery are not always optimized for precision tracking. The handoff between discovery and characterization must therefore be tightened. Automated pipelines should flag not only hyperbolic trajectories, but also statistically significant residuals from gravitational fits. These flags should trigger sustained observation campaigns even in the absence of visible activity. 3I/Atlas would likely have been less informative had its motion not been tracked with sufficient continuity. Temporal coverage is especially critical. Non-gravitational acceleration reveals itself cumulatively. Short observational arcs can mask it entirely or render it ambiguous. This means that interstellar objects should be followed for as long as feasible, including pre-perihelion and post-perihelion phases when possible. The cost of extended tracking must be weighed against the scientific return, but this case demonstrates that return can be substantial even when the object appears visually unremarkable. Another consequence lies in modelling practice. The default assumption of purely gravitational motion remains appropriate for the majority of small bodies, but should not be treated as sacrosanct when evidence suggests otherwise. Orbit determination frameworks must allow for flexible inclusion of non-gravitational terms and must report not only best-fit solutions, but also comparative fits across model classes. The distinction between detection and interpretation is crucial. One detects deviation before one explains it. This has epistemological significance. The analysis of 3I/Atlas illustrates a disciplined escalation of interpretation. Deviation was first identified, then verified, then modelled, and only then interpreted physically. This sequence matters. Reversing it invites bias. Future studies benefit from adopting this layered structure explicitly, particularly in cases where public or media attention may incentivize premature explanation. The object also highlights the importance of null results. The absence of a visible coma, the non-detection of gas emission lines, and the lack of extreme photometric variability are not failures, but constraints. In a regime where subtlety dominates upper limits can be as informative as detections. Observational programs should therefore be designed to quantify non-detections rigorously, rather than treating them as incidental. On the theoretical side, the analysis motivates refinement of low-activity outgassing models. Traditional cometry models are often tuned to objects with obvious coma and dust production. Extending these models to gas-dominated low-mass loss regimes is necessary. This includes better understanding of sublimation through porous mantles, anisotropy persistence under rotation, and the thermal evolution of small bodies over interstellar timescales. 3. I/Atlas does not demand new physics, but it does demand broader application of existing physics. The same applies to radiation pressure modelling. While judged less plausible here, radiation pressure remains a viable mechanism in principle. Improving constraints on object density, porosity, and structural integrity would sharpen discrimination between competing explanations. This requires coordinated optical and infrared observations as well as improved laboratory and numerical studies of aggregate behavior under interstellar and solar conditions. There are also implications for how uncertainty is communicated. The analysis has consistently avoided categorical claims where evidence does not support them. This is not merely stylistic restraint, it is methodological hygiene. Interstellar objects sit at the intersection of small sample statistics, strong selection effects, and public fascination. Overstated conclusions risk distorting both scientific understanding and public trust. 3. I/Atlas demonstrates that careful, bounded interpretation can still be compelling without exaggeration. At a deeper level, the object prompts reflection on how astronomy handles rarity. Rare events are not noise, they are probes of distribution tails. However, tails are treacherous. They can mislead when overgeneralized or ignored when inconvenient. The appropriate response is neither dismissal nor inflation but contextualization. This analysis has treated 3I/Atlas as neither representative nor exceptional by fiat but as informative within defined limits. This posture should become standard practice for transient low-number phenomena. The case also informs interdisciplinary dialogue. Planetary science, stellar dynamics, and galactic astrophysics all intersect in the study of interstellar objects. Traditionally, these fields operate with different assumptions and scales. Objects like 3I/Atlas force integration. Formation models must speak to ejection processes, which must speak to survival, which must speak to detection. No single subfield can fully interpret such an object in isolation. Looking ahead, the most transformative change will be statistical. As detection rates increase, the field will transition from narrative to distribution. Individual objects will still matter, but their significance will be measured against emerging populations. The interpretive weight placed on any single object will diminish, but the value of early exemplars will persist because they shape the questions asked of later data. 3. I/Atlas occupies that formative role. Finally, there is a conceptual consequence that transcends technical detail. The object reinforces a core scientific posture. Unfamiliarity does not imply anomaly in the fundamental sense. Nature is not obligated to produce objects that align with our expectations, especially when those expectations are based on limited local sampling. The correct response to novelty is neither astonishment nor dismissal, but disciplined curiosity. 3I/Atlas does not overturn models of small body dynamics, nor does it redefine interstellar matter. What it does is sharpen awareness of regimes previously underexplored. It reveals that the boundary between inert and active, between asteroid and comet, between local and interstellar is more continuous than categorical. This continuity is not a problem to be solved, but a reality to be incorporated. Enclosing the object's passage through the solar system is fleeting, but its methodological impact endures. It demonstrates the power of careful measurement, the necessity of layered inference, and the value of restraint in interpretation. It reminds us that the universe often speaks softly through small deviations rather than grand displays. Listening requires precision, patience, and humility. When those qualities are applied, even a subtle perturbation can illuminate a vast context. The final consideration is reflexive rather than additive. Having examined dynamics, mechanisms, implications, populations, and practiced the analysis, turns inward to address how meaning is assigned in conditions of partial knowledge. 3. I/Atlas functions not only as an astronomical object but as a test case for scientific reasoning under constraint. It exposes how inference is shaped by scarcity of data, how narratives emerge around anomalies, and how discipline is required to prevent explanation from outrunning evidence. This section therefore concerns epistemic posture, how conclusions should be held once drawn. A defining feature of this case is that the signal of interest is subtle. The acceleration is small, the activity invisible, the sample size minimal. There is no singular observation that compels a dramatic conclusion. Instead, meaning accumulates through consistency. This kind of evidence is easy to undervalue in environments conditioned to favour spectacle. Yet in many mature sciences, progress increasingly depends on resolving weak signals against complex backgrounds. The 3I/Atlas analysis exemplifies this mode. The work succeeds not by uncovering something loud, but by listening carefully to something quiet. Such cases reveal a tension between two scientific instincts. One is the instinct to normalize, to subsume new data under existing categories as quickly as possible. The other is the instinct to exceptionalize, to treat deviation as evidence of fundamental novelty. Both instincts are understandable, and both can mislead. Normalization risks erasing informative difference. Exceptionalization risks inventing difference where extension suffices. The analysis navigates between these by maintaining a third stance, contextualization. The object is neither forced into a familiar box nor elevated into a mystery. It is placed within a landscape of possibility defined by physics, probability, and limitation. This stance has practical consequences for how conclusions are framed. Throughout the analysis, language has been chosen to reflect degrees of confidence rather than binary claims. Terms such as consistent with favoured by and less plausible are not hedges but precision instruments. They encode relative support, not indecision. In an era where certainty is often expected or demanded, especially in public-facing science, such language can be misinterpreted as weakness. In fact, it is the opposite. It is an explicit representation of how knowledge actually accumulates. The case also demonstrates the asymmetry between detection and explanation. Detection can be firm, while explanation remains provisional. The non-gravitational acceleration of 3I/Atlas is robustly detected. The mechanism producing it is inferred with varying degrees of support. Conflating these two levels leads to confusion. One can accept the reality of the effect without committing to a specific cause. Maintaining that distinction is essential, particularly when alternative explanations carry vastly different implications. This asymmetry also applies temporally. Explanations that are weakly constrained today may become well constrained tomorrow, not because the object changes, but because tools improve. Infrared sensitivity, spectroscopic resolution survey cadence, and computational modelling are all advancing. The conclusions drawn here are therefore not endpoints but snapshots. They represent the best alignment between evidence and explanation given current capability. Treating them as provisional does not diminish their value, it preserves their adaptability. Another epistemic lesson concerns priors. Interpretation is never priors-free. Expectations about what interstellar objects should be like inevitably influence how data is read. Early expectations were shaped by solar system analogues. As interstellar detections accumulate, those priors must be updated. 3I/Atlas contributes to that update by demonstrating that low-activity, dynamically responsive bodies are possible. Future objects may reinforce or contradict this. The appropriate response is not to lock in a new expectation prematurely, but to widen the prior distribution. The object also clarifies the boundary between explanation and imagination. It is tempting when confronted with an unfamiliar object to explore speculative possibilities. Curiosity drives such exploration, and in some contexts it is productive. However, scientific explanation demands that speculation remain tethered. In this analysis, possibilities that extend beyond established physics were neither invoked nor required. This is not a dismissal of imagination, but an assertion of sequence. One must exhaust what is sufficient before reaching for what is extraordinary. The discipline shown here is especially important given the cultural context in which interstellar objects are discussed. These objects capture public imagination precisely because they arrive from elsewhere. That allure can distort judgment. The analysis implicitly argues that the correct scientific response to such allure is increased rigor, not reduced. The more an object invites narrative, the more carefully that narrative must be constrained. There is also a broader lesson about scale. Interstellar objects remind us that the solar system is not a closed laboratory. It is embedded in a galaxy full of processes that are similar in kind but diverse in outcome. The small body populations we see locally are the result of one formation history. Interstellar objects sample many. Expecting them to conform closely to local norms is statistically unlikely. Recognizing this reduces the perceived strangeness of objects like 3I/Atlas. What appears anomalous locally may be typical globally. The analysis therefore contributes to a shift in perspective. Instead of asking whether an interstellar object fits known categories, one asks what range of categories the galaxy produces. Instead of asking whether an object is active or inert, one asks how activity manifests across regimes of size, composition, and history. These are more generative questions. They lead away from classification anxiety and toward distributional understanding. Importantly, this shift does not weaken explanatory standards. On the contrary, it strengthens them by demanding that explanations operate across broader parameter spaces. The outgassing interpretation favoured here is not a retreat to convenience. It is an extension of known physics into a regime that had not previously been well sampled. This is how science grows, not by inventing new laws prematurely, but by discovering where old laws still apply. In closing the analysis, it is worth emphasizing proportionality. 3. I/Atlas is a small object with a small effect observed over a short time. Its significance lies not in overturning frameworks, but in refining them. It does not demand that we rethink gravity cometary physics or interstellar matter from first principles. It demands that we acknowledge continuity, subtlety, and diversity. The object passed through the solar system, was measured, analysed, and will depart. What remains is not a mystery, but a calibration. It calibrates expectations about interstellar debris, about detection bias, about low-level activity, and about the interpretive discipline required when data is sparse. These calibrations will quietly shape how the next object is received, studied, and understood. If there is a final takeaway, it is this: the universe often reveals itself not through surprises that shatter understanding, but through deviations that gently stretch it. Responding well to such deviations requires patience, humility, and methodological care. 3I/Atlas offered such a deviation. The analysis met it with proportionate response. That ultimately is the measure of success. The analysis can now be extended one final time, not by adding new empirical claims, but by examining durability. Scientific conclusions are not static objects. They persist, erode, or strengthen as contexts change. This section addresses what elements of the 3I/Atlas analysis are likely to remain stable over time, which are most vulnerable to revision, and how future developments may interact with the framework constructed here. The purpose is not to predict outcomes, but to assess structural resilience, which parts of the reasoning are foundational, and which are contingent. At the most durable level lies the dynamical detection itself, the identification of non-gravitational acceleration derived from independent datasets and confirmed through multiple analytical approaches is unlikely to be overturned barring discovery of a previously unknown systematic error. Such a reversal would require not merely improved data, but a fundamental reassessment of astrometric practice across observatories. While scientific humility demands openness to this possibility, its probability is low. The detection rests on mature techniques applied conservatively. As such, it constitutes the firmest layer of the analysis. Closely following in durability is the exclusion of several candidate mechanisms. Gravitational perturbations, solar wind pressure, electrostatic effects, and thermal recoil forces like Yarkovsky are ruled out not by narrow parameter tuning, but by orders of magnitude mismatch and directional inconsistency. These exclusions are robust because they depend on well-established physics with tightly constrained ranges. Future discoveries are unlikely to resurrect these mechanisms as viable explanations for the observed acceleration without simultaneously revising large portions of planetary dynamics. Less durable, but still relatively stable, is the comparative plausibility assessment between outgassing and radiation pressure. This judgment rests on current observational constraints, particularly the absence of extreme photometric variability and the lack of strong infrared anomalies. Improved observations could shift this balance. For example, detection of unusual thermal emission or refined shape constraints could strengthen radiation pressure scenarios. Conversely, direct detection of gas emission would strongly favour outgassing. This layer of the analysis is therefore conditional, not fragile. It is expected to evolve as data accumulates. More provisional still are inferences about composition structure and formation environment. These depend on models that integrate physics across vast timescales and unobservable histories. While these inferences are grounded in plausibility, they are inherently underdetermined. Multiple evolutionary pathways can lead to similar present-day behavior. Future interstellar detections may reveal alternative mechanisms of volatile retention or structural evolution prompting reinterpretation. This does not invalidate current inferences. It contextualizes them as best-fit explanations rather than unique solutions. The population-level implications occupy an intermediate position. The recognition of strong selection effects and detection bias is highly durable. These biases are structural features of observation and will persist even as instrumentation improves. What will change is the degree to which those biases dominate interpretation. As sample sizes grow, statistical leverage will increase, reducing reliance on individual exemplars. The conceptual shift advocated here away from categorical expectation and toward distributional thinking is therefore likely to strengthen rather than weaken over time. Methodologically, the layered structure of inference used in this analysis represents a durable template. Detection precedes verification, which precedes modeling, which precedes interpretation, which precedes contextualization. This sequence is not specific to 3i/Atlas. It is broadly applicable to rare transient phenomena across astronomy and beyond. Its value lies in preventing premature convergence on explanation. As such, it is likely to be adopted implicitly or explicitly in future work reinforcing its relevance. The analysis is more vulnerable in its descriptive language than in its logic. Terms such as interstellar comet low activity or intermediate regime are useful but imprecise. As new objects are discovered, taxonomy will evolve. Labels applied here may be retired or refined. This is a normal and healthy process. What matters is not the persistence of terminology, but the persistence of constraints and relationships. The object's behavior constrains what it can be regardless of what it is called. An important aspect of durability concerns public interpretation. While not directly addressed in technical analysis, it influences how conclusions are received and remembered. Simplified narratives often outlive nuanced ones. there is a risk that 3I/Atlas will be remembered either as unremarkable or as extraordinary, depending on narrative framing. Neither extreme captures the analysis. The durability of the correct interpretation depends on continued emphasis on proportionality and context. This is not guaranteed, but it is influenceable through careful communication. Looking forward, the arrival of next-generation surveys will test the framework developed here. Facilities with greater sensitivity and cadence will detect interstellar objects earlier and in greater numbers. Some will exhibit no detectable non-gravitational effects. Others will show stronger or different ones. The framework anticipates this diversity. It does not predict uniformity, it predicts spread. In this sense, it is falsifiable only if future objects consistently violate its assumptions about continuity and diversity. If future detections reveal that all interstellar objects are either strongly active or entirely inert, the intermediate regime highlighted here would require re-evaluation. If, however, a spectrum of behaviors emerges with 3I/Atlas, occupying one region of that spectrum, the analysis will have anticipated rather than lagged reality. This makes it a useful scaffold even if specific details change. Another dimension of durability concerns interdisciplinary relevance. The conclusions drawn here intersect with theories of planet formation, debris disk evolution, and galactic dynamics. These fields evolve at different rates. Insights about ejection mechanisms or volatile retention may be revised independently of small body dynamics. The analysis remains robust insofar as it does not depend on any single model, but rather on compatibility across multiple domains. This redundancy increases resilience. It is also worth noting that the analysis is conservative in what it leaves open. It does not exclude future surprises. It simply argues that none are currently required. This openness is a form of durability. Frameworks that foreclose possibility are brittle. Frameworks that accommodate extension without collapse are not. 3I/Atlas has been treated as an invitation to extension rather than a demand for revolution. In this sense, the object functions as a calibration point rather than a cornerstone. Removing it would not dismantle existing theories, but incorporating it refines them. Calibration points are often undervalued because they do not announce themselves loudly, yet they are essential for cumulative progress. They allow future data to be interpreted against a more accurately scaled background. As the object recedes into interstellar space, its immediate observational relevance ends. Its analytical relevance persists. It will be cited, compared, and reinterpreted as new objects appear. Some aspects of the analysis will age quickly, others slowly. The measure of its success will be whether future work engages with it critically, rather than dismissively building on its structure even as it revises its details. In conclusion, the endurance of the 3I/Atlas analysis lies not in any single claim but in its architecture. By separating detection from explanation, plausibility from certainty, and novelty from exception, it establishes a mode of reasoning well suited to a universe that offers limited data and vast diversity. This architecture is likely to outlast the specifics of the case that motivated it. The object itself was transient. The reasoning it prompted need not be.